All right, welcome back. So this session is more about, we're going to talk about the technology, basically the techniques for interconnection. I think this sort of goes into the next step after the peering. After you understand the peering and the economics, how do you actually engineer your network? Using BGP, what techniques do you use? How do you optimize your network for interconnection? Now, before I invite our next speaker, I just sort of like to take a minute to go through the session that we had earlier. And during the coffee break, one of the things we've been able to discuss, and I don't know whether this occurred to you, is that as you know, Africa has a number of languages. We have English, we have French, we have Spanish and Portuguese. Now, on the podium we had a French person and an English person, and they were supposed to negotiate peering. The first thing we observed was communication problem, because one speaks in French, the other one speaks in English. And so they need to go through an intermediary, somebody who understands both languages. Now, to me, that's as real as it gets for many network operators, and I can count the number of countries that I know, starting from Nigeria, Ghana, Zambia, who are neighboring either a French country to one of their borders, either on the north, east or south, or a Portuguese speaker on the north, east and south, and also for the Francophone and the Portuguese, they all have neighboring countries that speak a different language. So when it comes to peering, I think the fundamental barrier that exists even before you challenge the concept and the business and the technology is the language barrier. So that is going to be something that we have to deal with in this region to be able to overcome, at least start addressing the issue of peering. So next up is Andy Davidson from Allegro Networks and also LONAP, which is an exchange point in the UK. I'll let Andy speak more about that. And he's going to present on BGP traffic engineering for peering networks. And this is a technical presentation that will give you a view of how to design your network for BGP when you, or rather to implement BGP to peer with other networks. So, Andy?
Thank you very much, Machiki, and thank you for inviting me to present at this, which is my first AFPIP meeting. And it's really great to have already had so many interesting conversations and see so much enthusiasm for peering in Africa. So well done, and thanks for coming along and making some of these conversations happen, because I really do believe that interconnecting more widely will improve the performance and also reduce the cost of building your networks in Africa. As well as actually having the conversations and agreeing to interconnect, it's really important to configure your network in such a way that takes advantage of the interconnects in the framework that you exist in the continent. So I've put together an introduction tutorial which will follow now about how to do BGP traffic engineering once you've already agreed to peer. What do I mean by traffic engineering? If there are those in the room who are not completely familiar with that term, traffic engineering is a set of techniques that you can use to manage capacity demand, so your customers' demand on your network, and also ensure that you're running products of a high enough quality to be useful for your customers. Similarly, it also means that you configure your network in a way that allows you to predictably recover from failures that you have on the network, and mean that if you suffer a capacity outage, then you're able to continue to trade at the highest possible quality. And it's also a technique that you can use to manage the cost of capacity on your network. So it's a very, very important technique to deploy once the complexity of your network grows. What do I mean by that? Well, at the very, very beginning, when you build an ISP network, maybe in a single POP or a single town, managing capacity is relatively simple. You arrange peering in your city, and if you can send the traffic to a peer, you send the traffic to your peer. But what about when your network grows? What about if you connect to a second exchange point in the city, or if you go to another city altogether? What about when your capacity grows? You should be able to take advantage of the fact that your customers are sending you more traffic so that you can buy more effectively and configure your network more effectively to take advantage of the extra traffic and growth that you're having. Traffic engineering is not a new thing, it's something that all networks do, and I'm reflecting back on some of the challenges that I've faced over the last 10 years or so building BGP networks, and the challenges I've had to come around include circuits from the same POP that go into different places where the cost of capacity might be a difference of $100 a megabit. It may be $100 a megabit cheaper to send the traffic one way rather than the other. But the thing is, I've had a real reason to buy the more expensive capacity for a particular customer requirement or particular reach to another network. And I need at that point to configure my network in such a way that I'm really only using the expensive capacity when I really have to. Also, if you operate in an environment where there are a small number of ISPs who today are not yet willing to peer, you may have to work in your traffic engineering profile to get around the fact that you have poor connectivity to other ISPs in your country and good connectivity maybe to ISPs in a neighbouring country. But if a congestion is caused by the failure of one of your links, how do you make sure that service quality can be assured? And also, as your customers' demand changes, how do you cope with that? Customers 5 years ago were not so demanding in terms of video streaming in their homes or offices and the quality expectations that they have. Maybe your customers want to watch higher resolution videos. That means more bandwidth, and that means changing the way that you buy capacity and configure your routers to take advantage of that capacity. Now, this presentation isn't really about internal network traffic engineering, but I mention it because sometimes you have to, it's something you need to do, but it's much, much simpler than traffic engineering between different networks. And it's simple because on your internal network, you control both sides. So if you have a router in two different cities, you know exactly how much it costs you to send data between these cities, and you are in control of whether there's enough capacity to serve demand. And your IGP protocols, the things like OSPF, IS, have got tools that allow you to manage that cost and overlay availability, performance, and that sort of thing, so that you use the most effective link and the most cost-effective link. But inter-domain traffic engineering, i.e. when you're trying to handle the way that traffic moves between your network and somebody else's network, is much harder because you don't control both sides of the link. And the protocol we use to manage this, BGP, hides information about how much capacity is on the link and how much the link costs. So if you just simply configure BGP sessions with your neighbours and don't tune the performance or overlay your expectations, you may find that your network is not working as you expect. BGP exchanges the number of routes and prefix information, but it doesn't take into account the volume of traffic. So you may receive a very small number of routes from one network that delivers you a large amount of traffic. So you really need to overlay what your routers are expecting with real data about the volume of traffic and the cost of traffic. However, at the same time, even though inter-domain traffic engineering is hard, you'll likely find that most traffic with about where their traffic is going. And the way that you typically would do that is with demonstrating a tool called AS Stats that generates data on an AS by AS basis, which words you'll find in documentation here. It allows you to export information about packets routed through your network. It's normally sampled, so out of 100, 1,000 or 10,000 packets, depending on your size, you get a sample of just one of those flows so that it's a manageable amount of data. It's an average. You send this net flow information from your routers to a collector on your network, a box that you manage over UDP, and then you use a variety of either commercial or open source tools to sort and display the actual data from the flow records. So you export flow records that are sampled to a collector, and then you use a third-party tool to browse that data and generate reports, a little bit like AS Stats, which I mentioned a moment ago. You may find if you're using Cisco routers, then it's called NetFlow, but if you're using other routers, you may find that NetFlow is called something else. For example, Juniper call NetFlow JFlow, which is essentially, functionally, very, very similar. And you'll find that a NetFlow connector should be able to understand JFlow. There's a standards-based IETF effort called IPFix, which takes NetFlow 9 and builds slightly on that. I understand that many of the open source NetFlow v9 collectors will understand IPFix as well. And you may find that your vendor is using this NetFlow standard. And another standard called SFlow was built by a company called Inmon, who sell SFlow collectors, and typically that exports data from your layer 2 environment. Those are the different types of NetFlow. In the presentation, I've put a few examples of how to enable NetFlow on your network, which you can grab. You can grab the presentation from me afterwards and have a look. But essentially, you enable NetFlow on each interface at your edge. You configure the router to export NetFlow of a specific version, and I recommend you use version 9 because that will allow you to export IPv6 data as well. And you specify that you're interested in the origin AS rather than the peer AS, which is the origin AS is the network originating the traffic or consuming the traffic. And specify an interface on your router for the NetFlow to be sent from, and I recommend you use a loopback address so that it's always the same. In the presentation, courtesy of Nick Hilliard from the Irish Exchange, he's given me some NetFlow configuration examples for SUP 720s, which is slightly different to the generic example that I put on the slide before. So you can, if you're using 6500, 7600 based routers, you can use this example, and if you're using iOS XR based routers, there's another example here, again courtesy of Nick, that allows you to enable NetFlow on iOS XR devices. Crucially, the main difference with iOS XR is you also have to put an extra line under your router BGP config to say that BGP data should be exported with the flows. But these are in the presentation, you can grab them later. If for some reason you can't get NetFlow, for example, you are looking to build a network, maybe you are a e-commerce company, or like a hosted mail solution, etc., and you're sitting on somebody else's network right now, and you're trying to work out, is there value in me building a network, is there value in me peering? The other thing you can do to get data is analyze your log files. So if you're an e-commerce company, you might say, I want to peer with the eyeball networks so that I can give the highest possible quality of a service to my customers, but I don't know where my traffic is going because I don't have the AS data. The thing you can do is look in your logs, because you need to log the IP address that you're serving, the time and date, and the amount of traffic that you're serving, and you can aggregate those on an hour-by-hour basis to work out where you're sending traffic to, or where traffic or where requests are coming from, that you can then extrapolate to build actual per AS data as well. It's a lot more work than using NetFlow. So if you have a network already, I recommend you use NetFlow for this. But if you're evaluating whether to build a network, that's one way you can get some data. The last way to get data is not a very scientific way, but if you should have an instinct about where your traffic is going if you do run a network, but you can be fairly sure that your largest flows will be your local eyeball networks, your local access networks. And if you're a local access, then sure that a large amount of your flows are going to very large content networks. Now, you should still use NetFlow, but if you're trying to build a business case to build your network in such a way that it allows you to get NetFlow, or you want to have some early quick wins before refining the business case, you should be able to use your instinct to build a small number of peering sessions, demonstrate value, and then go ahead and build a better system for getting data. So that's those are some ways of building data. But the end result that you need is information about which ASs originate the most traffic to you, or which ASs consume the most traffic from you. When you have data, it will tell you your traffic direction. Are you mainly an inbound network? Does traffic mainly come to you? Or are you mainly an outbound network? Are you mainly sending traffic to other people? Or do you have a balanced network? Do you have a relatively similar amount of inbound and outbound traffic? And again, it tells you the top originators or the top destinations for your traffic. If you realise that you're a mainly outbound network, your life is a little bit easier because the tools that you have to shape traffic flow are somewhat more easy to use, and you can influence your outbound traffic direction on your routers. If you're mainly an inbound heavy network, your job is a little bit harder because you have to trick the way that other networks send traffic to you. So you're an inbound heavy router. The people who are sending the data have the most control. And the other inbound people's configuration changes, the configuration changes of a content network, for example, will influence what happens to your inbound traffic. The main tool that we have for influencing how traffic leaves a network is the BGP best path selection algorithm. And traffic engineering is all about understanding this process and causing this algorithm to do exactly what you want as a peering network. So you can influence when you receive a prefix from a peer or from a transit provider, you can put attributes on that, or you can actually you can put rules on the prefix that you learn which explain whether which exit is the most preferred, using local preference, a hard bit of configuration that we'll cover in a minute,